Hi, my name is Joshua Proctor. I'm going to be discussing a recently submitted article titled Generalizing Koopman Theory to Allow for Inputs and Control. This article is in review and can be found on the arXiv at this index number. This work's been done with my colleagues at the University of Washington, Steve Brunton in the Mechanical Engineering Department, and Nathan Kutz in the Applied Mathematics Department. I'm from the Institute for Disease Modeling in Bellevue, Washington. Now, one motivation for developing Koopman with inputs and control is the staggering number of preventable deaths that occur each year around the world. And we want to develop quantitative methods to help analyze infectious disease data, to help inform policy decisions, and allocate resources to hopefully prevent some of these deaths. Now, one of the major events of the 20th century guides at least my own motivation behind a lot of this, and that is the fact that we eradicated a human infectious disease, namely smallpox. And we're actually quite close to eradicating another disease, polio, hopefully in the next year or two. Now back to dynamical systems and Koopman operator theory. Now, this nonlinear dynamical system and dynamical system in general has had an enormous theoretical development over the last few decades, most of which has inherited quite a bit from a geometric perspective from Poincaré, at looking at these nonlinear vector fields. And there's been a tremendous number of different applications in a variety of scientific fields that have utilized these perspectives on things like normal forms, bifurcation theory, invariant sets, nonlinear manifolds, etc. But this geometric perspective can run into difficulty when the systems become very high dimensional and complex, or if you don't know the governing equations underlying the data that you're collecting, such as those in infectious disease problems. Now, for example, we can actually write down a heuristic set of equations called the susceptible, infected, and recovered. This has had tremendous success replicating epidemics and different types of endemic scenarios. But the more heterogeneity that you try to apply to these types of equations, for example, increasing by some characteristic I, you get a combinatorial explosion of states as well as parameters that need to be fit with data, and the normal tools of dynamical systems start to break down the higher dimensional you have. So instead of looking at these complex high dimensional nonlinear systems, we actually take an operator theoretic point of view. This is where Koopman operator theory comes in. That instead of looking at how this nonlinear system evolves, we actually look at how this linear operator K, called the Koopman operator, when applied to scalar valued functions G, and these G's are described as measuring something of the state, we can actually compose that with our nonlinear update, and what we get is actually a Koopman operator acting on an observable function, which then the observable function is evolved in time. So we actually get dynamics on data versus dynamics on states. What's interesting about this formulation is that you take something that's finite dimensional with nonlinear dynamics, you now get an infinite dimensional operator, K, this Koopman operator, but now it's linear. So we've traded this finite dimensional nonlinear system for an infinite dimensional linear system. Now this is interesting because now all of our linear tools for operators come into play, such as spectral analysis tools. Now here's an illustration of what we could potentially get if we have an approximation of that infinite dimensional operator K, denoted here by boldface K, such that if we knew what our underlying system was and how it was evolving according to these states, we would have access to the boldface F of our finite dimensional nonlinear system. But if all we have is measurements of our system, y1, y2, y3, if we can find a representation of this operator K, we can actually predict in the future using this linear operator. Now what does that look like in terms of an example? So let's take a nonlinear dynamical system. Here we have x dot 1 equal mu x1, but we have x dot 2 with a nonlinearity, x1 squared. Now we can actually linearize this system depending on the types of measurements we choose, or scalar functions. Now here our measurement is going to just be the identity, so x1 is y1 and x2 is y2, but we're going to add in a scalar valued observable function, which is x1 squared, giving us y3. Now, if we rewrite our nonlinear dynamical system according to these measurements, we can actually linearize that nonlinear system. Now, this is related to Kármán linearization, but we're framing it in terms of Koopman operator theory. And this is actually at the basis of another article where Steve Brunton is the first author and has been published in 2016 in PLOS One, and it's titled Koopman Invariant Subspaces. But this is an interesting perspective. You go from a nonlinear system to a linear system. Now, if you think about this a little bit, what's happened here is that we found a set of scalar valued observable functions that when we apply some operator k here, we actually stay within that subspace. So we've found this Koopman invariant subspace where each observable function can be written as a linear combination of the other measurement functions. Now, that's quite interesting, but what can we do with control? Well, let's say, for example, you have a nonlinear system. This is pretty much the same one that we saw previous. We have the Koopman linearized system, both of which now we've added an input. And now we want to apply some type of optimal control strategy, for example, a linear quadratic regulator cost function, and we want to drive the state of this system to an equilibrium value. So you can see x1 and x2, as well as the cost function over here. Now, typically you would linearize this nonlinear system around an equilibrium and develop your controller around that linearized system. But because we have a Koopman linear system, we can design a nonlinear optimal controller, and we get substantially better results using that Koopman nonlinear optimal controller versus linearizing our nonlinear system and applying a standard linear quadratic regulator. So this is kind of the hope behind a lot of the Koopman operator theory, is that by finding some representation where it's effectively linear, we can apply some of our traditional control strategies and design optimal controllers for a nonlinear system. Now, does this particular procedure work for all examples? Well, no, it doesn't, and there's a little bit of a trick here. So we have a center manifold equation where x dot equal x squared. Now let's say we apply the same methodology that I just gave in the previous example, and that is our first measurement function is just the identity, so y1 is x, but now we choose y2 as x squared. But when we take the derivative of y2, we actually get an x cubed out. So now as we start to build our Koopman linearized system, we actually do not get a closed invariant subspace, and we have to keep adding scalar observable functions to this set of equations. So we don't find a closed invariant subspace. So one conclusion from the first part of looking at this Koopman operator theory is that the selection of these appropriate observables is critical to get good reconstructions and approximations of that finite nonlinear system. Or you can just make sure that the set of observables is sufficiently large, or you just have a ton of data to look at these things. But typically what people do is called dynamic mode decomposition. You capture all the data you can from whatever experiment you have, you put it into state measurement snapshot matrices, form these into data matrices where each column is a particular time unit, each row is a particular state of the system, X is the current state snapshot matrix, and X prime is the future state snapshot matrix. And what we really want to find is an approximation of an operator A here that takes us from X to X prime. And this A, this DMD, dynamic mode decomposition A, is an approximation, hopefully, of the Koopman operator. Now, we've been talking a lot about Koopman operator theory and a little bit about DMD for autonomous systems. So what happens if you can add scalar observable functions to take your finite dimensional nonlinear system to an infinite dimensional linear system? We haven't talked much about inputs. How do we include inputs or control within the DMD architecture or within the Koopman architecture? Now, infectious disease in particular often comes with associated intervention data. For example, here is wild poliovirus type 1 over about 6 years, where each large tick mark is January, so the x-axis is time. On the y-axis here is a count of paralyzed children from polio. But down here, right below this graph where you see these purple marks, is actually vaccination campaigns, which are corresponding times. So each time there's a purple mark, there was a large vaccination campaign. So not only are there natural dynamics happening of how the disease is spreading, in this case through Nigeria, but there's also exogenous forcing to this dynamical system. As another example, we can look at the malaria incidence in all of Africa, and these are estimates from the Malaria Atlas Project from 2016. These are years 2010 to 2015, and also the exogenous input that was applied to Africa in the form of insecticide-treated bed nets and their distribution. So you can see that the incidence of malaria starts to go down in certain places and up in others, and you can see how it's related to the exogenous forcing. So in a different article, we published this paper, Dynamic Mode Decomposition with Control, in the SIAM Journal on Applied Dynamical Systems, that was focused on including inputs and exogenous forcing with DMD. Now that looks very similar to the previous image we have of DMD, but now we have a set of state measurements of our input, state measurements, and we have measurements of our input. Now combining these into our data matrices, again vectorizing a single snapshot matrix, but this is now the input at a particular time. We want to find two operators. One is the operator of A, and the other is the operator B. A is the effect of the state, the natural dynamics, and B is the transformation of our inputs to impact on the state. Now, Koopman and DMD are intimately related. Now, Rowley and Igor Mezic showed this in 2009, and we want to show now that Koopman can be generalized to include inputs and control, thus linking dynamic mode decomposition with the control to this more general framework. So, for example, let's consider now the non-autonomous dynamical system, x dot equal f of x comma u. Now we define the Koopman operator, now not only on these scalar valued observable functions that are dependent on x, but now these depend on both the state and the inputs. And this is defined to take us forward in time on the state. Now this star we're going to get back to because we can actually choose a number of points of definition here. But the important part is that now these scalar valued functions, g, depend both on x and u. We can expand this new Koopman operator with eigenfunctions that depend on x and u. Consider here with phi. And again, this is an infinite expansion on this infinite operator. And thus each vector-valued observable function, here denoted by bold-faced g, comprised of a lot of scalar-valued observable functions, can be described based on the eigenfunctions of our Koopman operator, and now these Koopman modes v. We can apply the Koopman operator to this vector-valued observable function, and we see that we get the same property out as the original Koopman operator theory on autonomous dynamical systems. Now, what does this mean, and how is it related to dynamic mode decomposition? Well, take, for example, a linear dynamical system, and we consider full state access and full input access by choosing observable functions that are the identity. So what does that mean? Each of our g's of our previous slide is now a state x or an input u. And we stack all of the states and inputs, and we start collecting data, and we find a finite dimensional approximation of our Koopman operator based on this matrix G. But this is a strange formulation for input-output systems. For example, rarely do people want to try to predict how u of k plus 1 is evolving in time. Often, you just want to know your input relationships, so your current state and your input, and how it affects your future state. So we could change the definition of this Koopman operator. So where that star was before, we can put a 0, such that when we apply the Koopman operator to this scalar valued observable function, we get the future state, but we no longer care about the future input. In the linear case, this transforms to something very similar to dynamic mode decomposition with control. So this actually collapses down to DMDc for the linear case. So this is actually an interesting innovation such that we can consider the following expansion of the Koopman operator to be different on the input versus the output side of this operator. What does that mean? Well, no longer do both sides of this expansion have the same eigenfunctions phi. We actually have psi, which are the left eigenfunctions of this Koopman operator, and phi are the right eigenfunctions. What that allows us to do is expand our future state in terms of a different set of eigenfunctions. Practically what that means is that the Koopman operator projects a large input space, which could be everything from inputs to states to cross terms like x times u, to a more restricted output space of only the linear observables that we're interested in. Now, as an example, we earlier discussed the importance of choosing the right observable functions for this Koopman linearized system, where we chose a new observable function y3, which is just x1 squared, and we had to include that as an output variable here. Now, for this situation, it closed nicely, and so we were able to develop optimal controllers for this scenario. But we could choose the correct observables on both the input and output side, such that we make sure to include the right y3 here, which is x1 squared, but we no longer care about how y3 evolves in time. And this is a slightly different perspective on how to use Koopman operator theory, and much more on approximating from data some type of operator that takes us from the correct measurements to the states we're interested in. So that's the end of this presentation. Again, this is from the recently submitted article, Generalizing Koopman Theory to Allow for Inputs and Control. Hope you enjoyed yourself. Thank you.